Okay, so regarding the previous thing, with Newton's second law, you'll find a number of homework problems, and you should certainly look back at the old exams and practice that. Um, but that is the basic idea. Now, let's move on to rotational kinetic energy. Now, in linear motion, the kinetic energy was given as K equals 1/2 mv squared. Remember, we're making these analogs. That is, that x is becoming theta, v is becoming omega, a is becoming alpha. Then we had F is becoming tau for torque. Mass is becoming I for moments of inertia. And so it shouldn't be that hard for you to see here that my mass can be replaced with the moments of inertia, and V can be replaced with omega. And then we get something like this. We get the kinetic energy equals 1/2 of I omega squared. In fact, this is where the definition of the moment of inertia is derived from. We're not going to get into it here. But this is how we find the kinetic energy of a rotating body. So if I have a body that's rotating but not moving in a straight line, it has a certain amount of energy that's associated with that motion, and it's just equal to the moment of inertia times omega squared. So let me just say this in words. The mass, which is a measure of the object's inertia, is replaced with the moment of inertia, which is a measure of the object's rotational inertia. Rotational inertia. And the velocity, which we usually have in kinetic energy, is replaced with the angular velocity. Now, just as we had before, chapter 5, I think, the work-energy theorem says that when you do work on an object, you increase its energy. So this is also going to apply here. It's also going to apply to rotating objects. All right, let's do a quick example, and then you'll have some more examples in your homework. So how much work is required to stop a thin hoop rotating at 10 radians per second? And I give the mass and the radius of the hoop. And then if the hoop is slowed to rest in 5 seconds, how much power was expended? All right, well, I want to know the amount of work required. I know that my work will cause the energy to change. So whatever energy it has right now, I want to expend enough work to take away that energy. And so the work then will equal the amount of kinetic energy that it has right now. That's 1/2 I omega squared. That's 1/2. Let's see, let's figure out what our I is. Now this is a hoop, so it has a moment of inertia, mr squared. You'd go back to that table, find the appropriate object. This is a thin hoop, and the moment of inertia is mr squared. So it has a mass of 1 kilogram, a radius of 1 meter. Obviously, that's 1 kilogram meter squared. And then omega is moving at 10 radians per second. You always want to have this in radians. So this should always be in radians. That is the SI unit, especially in these problems when we're using Newton's second law, when we're looking at the energy of an object, and when we're looking at the momentum, which will come next. You always want to know the angular quantities in radians, and that's squared. So the amount of energy is 1/2 of 1 times 100. That's 50 joules, and that's the answer to the question. It requires 50 joules of work in order to stop it. Now, the other question is, if the hoop is slowed to rest in 5 seconds, how much power was expended? Well, I know that power is just work over time. So that's 50 joules over 5 seconds, which is 10 watts. 10 watts. Okay, y'all try this. This quick test actually goes back to the previous problem with Newton's second law. But y'all try this. Remember, you're going to have something like the sum of the torques equals I times alpha. And then we're looking for the angular speed. Once you find alpha, First, you have to find the sum of the torques and the moments of inertia. And once you find alpha, then you can find your angular speed. I'll leave that for you to try on your own. And then the next topic will be the last topic for this chapter.